As you can see, this is our project. This is the board, and on the left side we have all the power and ground setup connected all around like this. And so when we set the input to 50 Hertz at 5 volts peak to peak, and we follow the leads, we're feeding it into our very own inverter. And the output, when we take the output, we can see when we visualize both the input and output, it is indeed correctly inverting the input. So this is how our inverter works properly. The yellow channel is the input and the blue channel is the output. Here we're looking at the summer. So the input is set as 60 Hertz and 3 volts peak to peak. Here you can see that we're taking both of them and we're feeding it both into these potentiometers, both set to 5 kilo ohms. And because the other RF is set to 10 kilo ohms, this gives a gain of 2 for each of these inputs, which means this has a total gain, since both inputs are the same, of 4. Since it's set to 3 volts peak to peak, as you can see here, the output is 3 times 4, about 12 volts max. And this shows, and while there is some variation, this could be accounted by the fact that it is determined by how we set the potentiometers. And while it may look like it's the same, any slight twist is almost a factor of 10 change. So this is to show that the summer works as intended. Furthermore, if we change up the design and have the 3 volts peak to peak come in, and while it's multiplied by 2, we have the other end go invert first and then come back. So we're subtracting by the same signal. We should in theory get an output that's about 0. And just as we predicted, we get a 3 volts for channel 1 and 600 millivolts. And again, like I said, the difference can be accounted due to the potentiometer values. This shows that subtraction can indeed be performed using our computer. Now we are testing the integration of this system. So when we set our input to a sine wave at 26 Hertz, we get an output with the unity gain and the input signal integrated. Originally, we started at 50 Hertz. However, due to the capacitor having variable, or the capacitor's impedance depend on the frequency, the unity gain was determined to be 26 Hertz by trial and error. It means that the gain is dependent on the frequency. Going down, there's a greater. However, as I increase the frequency, it starts decreasing. And of course, this output of the integrator is inverted due to the use of inverting terminal. For the square wave, however, it was determined to be 40 Hertz. As you can see, 40 Hertz square wave produces a triangle wave with the same unity gain at 40 Hertz. And this was again determined by trial and error. For the differentiator, it was also experimentally determined that when the input is a ramp wave, and for the proper output to have a unity gain, it must be at 80 Hertz. For sine wave, it's approximately 52 Hertz for the output to have a unity gain. Therefore, we have determined the optimal conditions for our differentiator to work in.
So that's our diagram. Can you pull up our simulation? Here's our actual circuit that we built. Here's the function generator and our input and DC power supply. And then here is our, the input is in yellow and the output is in blue.
Yeah.
And this is what the simulation looks like. And as you can see, it's very close to what we see on the oscilloscope. So that's our diagram. Can you pull up our simulation? Here's our actual circuit that we built. Here's the function generator and our input and DC power supply. And then here is our, the input is in yellow and the output is in blue.
Yeah.
And this is what the simulation looks like. And as you can see, it's very close to what we see on the oscilloscope.